Good morning, everybody. Thank you for this chance to be with you through this conference. My name is Youmn Al Rawi. I will be presenting my work, Finite Element Analysis of Inverted L-Shaped Beam Column Joints in Special Moment Resisting Frame, which is a nonlinear analysis using Abaqus. Through the outline, we will go and see that we are going to talk about an introduction, literature review, work methodology, results and discussion, conclusion, and reference at the end. Why beam column joints matter under seismic loading. In a special moment resisting frame, beam column joints transfer moments, shear, and axial load between members. During earthquakes, joints are loaded into the inelastic range through repeated load reversals. That's why joint failure is typically brittle and not ductile, and it can trigger collapse of the entire frame. Joint behavior is therefore central to seismic performance and life safety design. Now, what was our research about and what was the objective of the research? The research is about inverted L-shaped joints that are uniquely vulnerable. They sit at the roof exterior location where the slab and one beam are absent. The result is geometric discontinuity at the joint core, asymmetric and reverse moment transfer, limited anchorage length for beam bars, and higher risk of brittle joint shear failure. Now, the objectives of the research was to build a nonlinear finite element model through Abaqus, and this model was for the inverted L joint with realistic detailing, apply the concrete damage plasticity model, compare two concrete grades, F'C 29.1 and F'C 50 megapascal, sweep for load magnitudes 1, 0.75, 0.5, and 0.25. Extract displacements, reaction forces, stresses to inform detailing. Now, through the literature review, there were many documents talking about special moment resisting frame. If we want to specify what is a special moment resisting frame, we can say that for each beam and column connection, there is a certain resistance for the lateral load, primarily through flexural, with detailing chosen to deliver large inelastic deformation capacity. And this special moment resisting frame is designed to develop a plastic hinge in the beam, reaches large drift without losing gravity capacity, and used for seismic regions where ductility, not strength alone, governs the survival. The strong column and weak beam philosophy is the main issue of an elastic hinge. Plastic hinges must form in beams and not in columns. Why? We have to avoid soft story collapse. If columns yield first, an entire story can collapse vertically and brittle failure with no warning. And how are we going to make the plastic hinge inside the beam and not the column? According to ACI code, it enforces the column beam flexural strength ratio to be 1.2 summation of the beam moment should be less than or equal to the summation of the moments in the column, so the beam will yield first at every joint. Now, the result will be distributed energy dissipation, hinges spread across many beams, and the frame deforms ductily, absorbs energy, and survives. Now, classification of beam column joints can be classified as interior, exterior, or corner, where the interior has 4 frame members, which is the best confinement. The exterior has 3 members, 1 bar must be anchored, and the corner has 2 members in plane and very limited confinement. While if we are talking about the roof, which is the case of our study, we have top story where the column stops, And now we are talking about interior, exterior, and corner without continuation of the upper column. How can a beam column joint fail? Usually, this failure happens with joint shear failure, as joint shear failure, for example, diagonal cracking through the joint core, brittle and most dangerous, or bond or to anchorage slippage where the beam bars pull out of when development length is insufficient, or beam hinging, desired ductile mechanism, flexural yielding at the beam and column hinging. Column hinging is undesirable and can yield for soft story collapse. Now, key detailing concepts from the ACI code ensures the following. We have to assure confinement where closed stirrups and closely spaced stirrups at the connection. Anchorage, adequate development length should be used. Capacity, design, strong column and weak beam as we mentioned previously, and joist shear where the code limits on joint shear stress prevent diagonal cracking of the joint core. Now, why the inverted L joint is critical? It is the least confined, least redundant joint in a moment frame, yet it is exactly where the exterior columns meet the top story beam. There is no column above the confinement of the joint core from above. Only one beam frame in force transfer is asymmetric, and the anchorage of the beam bars is limited by the column depth alone. Now, through the research, we have followed the following methodology. We assigned the geometry, the reinforcement, the material. We did the finite element model, assigned the boundary conditions and the loading, and then ran the model and found the outputs that we are going to discuss, which are the displacement, reaction forces, and the principal stresses. For the geometry, we chose a beam of 1.5 meters and a column of 3 meters. The section for both the beams and the columns was chosen to be 300 times 300 millimeter. The joint was an L inverted section with roof exterior, and the model was done through Abaqus. For the reinforcement details, the column modeled was 8 phi 16 longitudinal bars, and stirrups were phi 10 spaced at 75 millimeters. For the beam, the top reinforcement were phi 16, 2 bars phi 16, and the bottom were 2 bar phi 16. And the stirrups were phi 8 spaced at 75 millimeter near the joint and 150 millimeter away from the joint. For the modeling for concrete and steel, for the concrete damage plasticity model of the concrete were used for F'(C) 29.1 and F'(C) 50 megapascal. For the steel, the elastic plastic with isotropic hardening was used with F yield 420 megapascal. We started by the model through Abaqus explicit, modeled the concrete material that we need, added the rebars, and then ran the software to get our results. We added also the boundary conditions where the column was fully fixed at the base, and we added at the beam tip a roller restraint preventing horizontal displacement only. The load pressure was varied from 0.25 to 1, which was assigning the lateral load. Now, for F'(C) used, the comparison was based between 29.1 and 50 MPa, and for the various types of loading varying from 0.25 to 1. The results that we are going to discuss, the displacement, the reaction forces, and and the stresses. As for the displacement, we have noticed that the displacement with the models related to higher F'C showed a lower displacement, which is 40.32 millimeters compared to that of the lower F'C, which was 45.39 millimeter. Higher F'C showed a stiffer joint and a smaller drift, which is 11% reduction in the lateral drift by the stiffening of the concrete. While comparing the reaction forces, we have noticed the following, that despite whatever change in the F'C characteristics, the peak vertical reaction was nearly the same, with a slight difference of about 0.1%, confirming that the force transfer through the joint is governed by the geometry and detailing and not by the concrete strength itself. For the peak axial stress S11 versus the load magnitude, we noticed that nearly the values were close for 0.25, 0.5, and 0.75, but for the value of 1 as a magnitude, there was an increase of 10% for the higher F'C, with a stress value equal to 2,640 megapascal, while that corresponding to the lower F'C, which was equal to 2,407 megapascal. For summary for the results, we can notice that the displacement showed a lower displacement as mentioned previously for the higher F'C compared to the stresses that showed higher stress for the higher reinforcement. So we can summarize the following, that displacement dropped for the higher F'C. For the shear reactions, they stayed nearly the same. For the stress distribution, the stress rises with the higher F'C for the concrete. As a summary of the displacement and stresses as well, we can say out of plane displacement U3 and transfer stresses S22 and S33 stay in the order of magnitude below the dominant in plane component, confirming a clean plan joint response under the applied vertical pressure. While the inverted L joint behavior essentially as a 2D plane frame node, justifying the in-plane assessment used throughout this study. So we can clearly see here that the displacement versus the reaction showed the same assessment as previously mentioned, that for the 50 megapascal, the joint deformed less at every magnitude, but the same stiffness gain that limits drift also concentrates stress in the same joint. Both curves remain approximately linear with the magnitude, meaning that the joint stays in a serviceable regime up to the design load, but with a reduced reverse in the high strength case. So we can conclude that the concrete strength alone cannot replace the conformity. What changing F'C does and does not fix. Changing F'C, we can say that it can help us reduce the peak lateral drift load, lower elastic deformation across all magnitude, improve control of the cracking with width under service load, higher modulus of elasticity, meaning a smaller member deflection globally. While higher F'C does not fix is the peak tensile stress S11, which was increased by 10%, causing a brittle failure more than the lower F'C. Reaction forces are essentially unchanged and the load path is unaltered. Anchorage demands on beam bars remain the same, and confinement hoops and detailing still govern the seismic safety. In conclusion, we can say that the nonlinear finite element analysis through Abaqus captures the response of the inverted L joint. Higher strength concrete reduces the drift but raises the stress concentration. Global force transfer is governed by geometry and detailing, not by F'(C), and confinement hoops and anchorage remain the primary tools for seismic safety. These are our references for the research. Thank you for your attention and thank you for this chance to be with you throughout this conference.